This is FlippedHarber for physics. In this video, we're going to go over the practice problems on page 67, numbers 22 through 25. Number 22 says use figure 311 to determine the velocity of an airplane that is speeding up at each of the following times: 1 second, 2 seconds, and 2.5 seconds. Now, since they're giving us a velocity time graph in figure 311, really we just need to read the velocities from the graph at the appropriate time. Pretty straightforward. At 1 second, the airplane is going 74 meters per second. At 2 seconds, the airplane is going 78 meters per second. And at 2.5 seconds, the airplane is going 80 meters per second. Moving on to number 23, it asks us to use dimensional analysis to convert an airplane speed from 75 meters per second to kilometers per hour. So the way we're going to accomplish this is we're actually going to multiply 75 meters per second by two fractions. Our first fraction is going to change the meters into kilometers. So I make sure that I put kilometers on top and meters on bottom. And in 1 kilometer, there's 1,000 meters. So this fraction says to divide by 1,000 in order to make it kilometers on top. Our second fraction is going to change that seconds to hours. So now I need to make sure that seconds are on top so that they cancel with the seconds that are in meters per second. That's going to put hours in the bottom of that fraction. So in 1 hour, there are 3,600 seconds. Now the way I got that is there's 60 minutes in an hour and 60 seconds in an hour. So if you multiply 60 times 60, you get 3,600. So really all we do is grab a calculator and take 75, divide it by 1,000, and multiply it by 3,600. We end up with 270 kilometers per hour. Number 24 gives us a position time graph. It says a position time graph for a pony running in a field is shown in figure 312. Draw the corresponding velocity time graph using the same time scale. So basically, they want us to make a velocity time graph that is laid out with the time axis the same length, and everything should kind of line up. Now, what I need to do in order to find velocity from this displacement time graph is to look at the slope of the green curve. Now, if you go on to calculus, you develop this skill pretty easily to where you can talk about the slopes of a curve all the way through. But because we haven't gone through calculus, what I'd like to do is kind of cover up all but a thin little portion of the displacement time graph so that we can talk about just a little itty bitty chunk of the graph so that we can talk about just that little chunk of slope. Okay, and this is that skill that you develop in calculus. But if we look at the very beginning of the displacement time graph, so I've got everything covered up, but just the absolute little first bit of the displacement time graph, we see that the slope is 0. So that slope of the displacement time graph is my velocity. So I actually put a point at 0 on my velocity time graph at that very beginning. Now, as I move across the scale, we see that the slope changes a little bit with each little chunk that we expose. So now that displacement curve is pointing down just a little bit. So it's just a little bit negative. So I plot a red dot for velocity because my velocity time graphs are red. So I plot a little red dot just below the time axis, meaning that it's a slight negative velocity. Moving over a little bit more, we see that the slope is a little more negative. So we plot a point that's a little more negative on the velocity time graph. And we keep on doing this, going across, seeing that the velocity goes down and down and down. And then we work our way all the way across the graph and we end up with a series of dots like this. Now the purpose behind the blue line is to try to signify, some kind of important spot in the graph. Just kind of like where it might be the steepest or it's closest to be the steepest. So you should kind of smooth out these dots a little bit into a nice smooth curve. All right, let's move on to number 25. A car is driven at a constant velocity of 25 meters per second for 10 minutes. The car runs out of gas and the driver walks in the same direction at 1.5 meters per second for 20 minutes to the nearest gas station. The driver takes 2 minutes to fill a gas can, then walks back to the car at 1.2 meters per second, and eventually drives at 25 meters per second in the opposite direction than that of the original trip. They want us to draw a velocity time graph using seconds as our time unit. So we need to change all of these minutes into seconds. We need to calculate the distance the driver walked to the gas station to find the time it took for him to walk back to the car, because we know how long it took him to drive to the gas station. And when he walks back, it's going to be the same distance, but they didn't tell us the time. And then they want us to draw a position time graph for the situation using the areas under the velocity time graph. All right, so our first job is to draw a velocity time graph, and what we want to do is change all of these times into seconds. So the 10 minutes that he was driving turns into 600 seconds. The 20 minutes that he was walking would turn into 1200 seconds. The 2 minutes that he's filling up the gas can is 120 seconds. So that leaves the time walking back to the car. We need to figure out how long it takes for him to walk back to the car. Now, multiplying our distance times our time, we find out that he walks a distance of 1,800 meters, that's 1.8 kilometers, to the gas station. So he's going to walk the same distance back. So we're going to use this distance back, divide by his 1.2 meters per second. Obviously, he was a little downtrodden on the trip back and walked a little bit slower, so it took him 1,500 seconds to get back to his car. So now we're all set to make this velocity time graph using our velocities and our new times here. We should end up with a total time of 3,420 seconds. Really simply, I just added up all the times. So we see our first chunk of this velocity time graph is very high. He's driving. He's going 25 meters per second at a constant velocity. So we have that first chunk of his motion. Didn't take that long. It was only 10 minutes, 600 seconds. And then that vertical line down, basically that's where he ran out of gas. And then that wider but much lower horizontal chunk is when he's walking to the gas station. And then we've got a chunk where he's at the gas station. He's not moving for 2 minutes. So that velocity is 0 for that 2 minutes. And then it dips below the time axis. It goes into a negative velocity because he's walking back to the car. He's walking in the opposite direction. So that should all add up to my 3,420 seconds. Okay, so now that we've got our velocity time graph, now we need to actually use it. And one feature that's handy about velocity time graphs is the area under the velocity time graph tells us our displacement for that time. So I want to actually find my areas under these red lines, which isn't that bad because these are all rectangles. So all I need to do is multiply a width times a height. That width is really my time. My height is my velocity. Whenever you multiply velocity times time, you get a displacement. So that's why the area under the velocity time graph is equal to our displacement. So let's start finding these areas. Our first area, 25 meters per second, is our height. We multiply by our width of 600 seconds. We get 15,000 meters. That's 15 kilometers. So he drove 15 kilometers. He runs out of gas. He walks at 1.5 meters per second. That's the height of our second chunk. 1,200 seconds is the width of that rectangle. He goes 1.8 kilometers. We kind of already knew that, but here it is as an area calculation. Now, the chunk where he's at the gas station has no area because the height of that rectangle, the velocity, is 0. So when the velocity is 0, there's no area under the curve. So we don't, I didn't bother to show a calculation for that. Now, this is going to be a little bit weird. in calculus, in physics, when we're doing these areas under curves, because this is a very calc-like thing, there's such a thing as a negative area. Because we have this negative velocity, we can actually talk about that as a negative height. That sounds very weird, I know. But we let the math take care of us like this. We use that negative height. It tells us that he's walking backwards, and we've got a negative displacement of 1.8 kilometers. So we're going to use all of these displacements in order to make our displacement time graph. So our first chunk of the displacement time graph, he needs to cover 15 kilometers. So we draw a green line, because it's displacement time, that goes from 0 up to 15 kilometers in the appropriate amount of time. Then he goes 1.8 kilometers, so much shorter displacement. He does it in a much longer time, so my next line goes only 1.8 kilometers higher, but it goes over 1200 seconds. Little horizontal chunk, that's where he's not changing his position. He's at the gas station. We're just taking that to be a 0 displacement. And then this last chunk, he's going back to the car. So, you could kind of mark on the y-axis where the car is, and that line needs to go back down. That is, he's walking back to the car. All right, so there's our displacement time graph, all from the areas under a velocity time graph. Okay, so that's it. I hope these practice problems are helping you. That's the idea. So it's time to get to work. I'll see you in class, and I'll see you online.